Hello, everybody, and welcome to episode 43 of Diabetics for Diabetics Radio. Today's episode is titled Mapping Out Autoimmunity in Type 1 Diabetes. We are going to look at the nitty-gritty details of how Type 1 diabetes orchestrates its inflammatory storm, or rather, what is the inflammatory storm that is orchestrating Type 1 diabetes? Now, if we haven't met yet, my name is Bowie. I've had type 1 diabetes, I need to correct this, for 23 years. I just recently had my diabetiversary back in August. It's September currently. And so 23 years with type 1 diabetes, healing my diabetes naturally and sharing what I'm learning on this journey as I go. About 2 years ago, I just had this epiphany and decided I don't want to do this anymore. I don't want to have this anymore. All of the resources I have at my disposal, I had at the time, endocrinologists and doctors and what have you, none of them were doing what I saw as enough. And so I decided to kind of take that all into my own hands. And in researching homeopathic medicine, naturopathic medicine, supplements, food quality, all of those things, I have slowly peeled back the levels of everything that goes into type 1 diabetes. And I've been sharing on this journey all along. So follow along on TikTok. That's my main social media platform. If you're not already subscribed here on YouTube, subscribe here. And let's go ahead and get started. So in this episode, we're going to look at how autoimmunity comes about, specifically for diabetes, but we can expand in a number of different directions as to kind of what this looks like in a normal system versus just an autoimmune, any run-of-the-mill autoimmune condition. We're going to look at the relationships between the specific inflammatory molecules, the signals and the cascades that they initiate in the body, how our body regulates them, how they may not in terms of disease. And we'll compare all of this to what we would expect from a healthy system. And so with these comparisons, we'll have windows of opportunity where we can possibly make adjustments to improve our body's ability to function from an immune standpoint, from a balance standpoint, from a dysfunction standpoint. I've also got a map, a physical map where you can kind of look a flow chart of sorts where you can look and see what all of this looks like. And some people are visual learners as opposed to being spoken to. I'm one of those, so we'll include all of that in this episode. So let's quickly reflect back on episode 42, where we gave an introduction to the specific molecules behind inflammation, and as well as some of the possible combinations of origins of type 1 diabetes. So genes, nutrients, pathogens, they all induce their own inflammatory markers. And so when you're looking at our natural immunity in the context of disease, where are these inflammatory markers coming from? Who are these outlaws? Who's on the wanted poster when we find out that we have type 1 diabetes? A lot of people new to the disease and those with it 20 plus years never really ever get the details as to what's going on. And I found that when I learn about this stuff, a lot more actionable steps start to become apparent. And so that's why we're at where we're at. So this is the list we went over in episode 42. If you want the rundown on each of these, head to episode 42 and get your fix to make sure we know what all of these players are. This is not comprehensive. I know for sure the interleukins, there's like 20 to 30 of them. these are just some of the, the major players in the diabetic realm. But what we really want to know now is, how do they all fit together? And this painting here is by a local artist, and he painted this after coming down with a cancer diagnosis, and it's just incredible. He's an amazing artist. His name's Isaac Abrams, but I just think it's a wonderful vision, imagery of what's going on in our body, the complexity, the colors, the shapes, the layering, and everything. I think it's just kind of out of this world, and very cool. So let's see how all of these inflammatory markers fit. Okay, so here's our list. Okay, lock it in. We're going to take a look at all of them. So when we think about our immune system, right, there's a bunch of different levels to it. Our first is obviously barriers. The goal of our immunity is to keep everything out so that nothing has to be reacted on. This is our skin, our mucus, our tears, our stomach, digesting things and getting rid of it through our GI tract. These are the things on the outside, closest to the outside, that keep things away. Now, when I was putting this together, I was tempted to put our lymphatic system as our first line of defense, but that is not technically true. It is our innate immune system, which is the second line of defense. So in the context of how this progresses in diabetes, there is some sort of triggering event, right? That barrier is broken. Whether from the inside or from the outside, there is something that is not like going right. And this could be from genetics, it could be from nutrients, it could be from pathogens like parasites, virus, bacteria. Probably a combination of all three in terms of our susceptibility to either and all. So it's interesting that they each have an impact on each other. You can have pathogens that affect genetic expression. You can have genetic expressions that make you more susceptible to either nutrient deficiencies or pathogens. You can have pre-existing nutrient deficiencies that impact genetic expression. You can have, nutrient deficiencies that impact your susceptibility to pathogens. Pathogens can rob our bodies of nutrients and cause deficiencies that lead to genetic deficiencies. So it's a wide, interconnected web. So this is just kind of off the top of my head list of possible root cause influences. It could be genetic. You think of the HLA complex. HLA stands for human leukocyte antigen, and I cover this in earlier episodes of the podcast. But they are clusters of genes that are responsible for the proper functioning of our immune system, the proper identification of self versus not self, which is at the root of that kind of autoimmune theory of diabetes, thinking that, our immune system improperly identified beta cells as something else and need that as a threat, when in reality it was ourself. HLA complex, that's where that all happens. The HFE gene, this is specific to iron regulation. My passion, and again, a lot of the episodes of the podcast from before are focused on iron regulation and the downstream effects of iron dysregulation in the body. There's a huge, huge connection between iron utilization in the body and the development of diabetes. The HFE gene is one of the main ones tied to iron regulation. That's the gene associated with hereditary hemochromatosis. But know that even if you don't have these genes, there are such thing as carriers. There are such thing as subtypes within this HFE gene, different parts of different genes. So H63D and C282Y are different variants within the HFE gene that can influence your body's retention of iron. You may just be genetically inclined towards improper beta cell function. Your body may not have the proper mechanisms in place to repair DNA. And so when something goes awry, our body isn't able to fix it, right? And that usually stems from environmental and nutritional conditions. So nutrient deficiencies, being low in magnesium, being high in iron, low in copper, low in the fat soluble vitamins, these affect organ function. When our organs can't do what they need to, the cellular environments are compromised. And this can affect gene expression. This can impact opportunistic pathogens. It's coming from our diet. It's coming from our ability to handle stress, the fact that our nervous system is always on and cannot properly rest. And then when you think about it from a pathogenic standpoint, Epstein-Barr virus, our vaccinations, COVID, parasites, Lyme disease, and the bacteria associated with that, they all have roles in influencing our immune system and our organ systems for attack on beta cells. And so now that we have all of, whether it be gene, environment, pathogen, something's going on and our body is now identified and locked on an invader, an enemy, right? So what happens now? Our body has a series of cells called antigen presenting cells. And you see there at the bottom, they're typically of two main types, dendritic cells and macrophages. So these are like the local police force. They are scouts that are kind of in and of the neighborhoods in the cells looking for possible invaders and enemies. What happens when they find it? They latch onto it, they swallow it, they engulf it, and they keep a little relic of what they've engulfed to present to the major histocompatibility complex, the NHC molecules. And this is basically saying, like, look who I found, look who I found. We need to make sure that we take care of, what I've just identified. This presenting of the antigen, right? The APC activation, like engulfing the invader and latching onto the MHC, initiates its own smaller degree of the immune system. This is our innate immune system. So this is kind of like internal affairs, little bit of a smaller scale than our adaptive immune system, which comes later on. So inflammatory molecules like interferon gamma, tumor necrosis factor alpha, and interleukin 1b, these are all activated commensurate to the threat level detected, right? These, it's really a matter more of quantity, right? The more of a threat we have, the more these cytokines. I don't want you to think that just because any of these are present, something is wrong. There's cytokines present all the time, right? Just for basic cell function in terms of like taking out the trash, all of the byproducts of our metabolism. However, in more serious states where those scout cells find something a little bit more significant and start to sound the alarm for more, that is when these cytokines start to really take action. And you see the second bullet point here, NFKB. This is a transcription factor. A transcription factor is something that flips switches on and off in our genes. So NFKB, when it recognizes that there are increased levels of cytokines like IFNY, TNFA, IL-1B, they will start to turn the genes on that are responsible for making more of those cytokines. The more these cytokines are present, the higher the likelihood that the MHC detection for antigens, right? Like, so I want to make sure I get this right. So MHC is they're like little sensors on the surfaces of cells. And when all of these cytokines are present, it increases the number of sensors. So our sensitivity to the antigens that have been found increases. So this kind of like puts everyone on high alert, like, hey, there's something in the water here. We need to make sure that we're paying attention. That's what's going on in this innate immune system reaction. As part of that innate immune reaction, we also have kind of a separate set of immune cells called natural killer cells. This is like our frontline defense, our, the sheriff of each cell. They patrol the cells. This is like basic mundane function. Like if something in the cell is slowing down or dying, aging out, the natural killer cells come in, package it up to help get rid of it so that new ones can come in and continue doing the job, right? The natural killer cells are a critical part of our natural immunity, right? They're kind of the ones that make sure that our cells don't age out and break down, and they keep things running smoothly. Now, in the context of autoimmunity, natural killer cells have been shown to dysfunction a little bit, right? And there's a couple of ways where that happens. Either they can't handle the amount of dysfunction that's going on and they're kind of like being overrun, or they're a part of the issue in attacking self tissue as opposed to as attacking healthy tissue instead of the aging out tissue, right? Like maybe they're a little overactive and they're doing too much. So, natural killer cells. Now, I wanted to retouch on the major histocompatibility complex because it's important on how the immune cascade continues. There are two classes of MHC molecules. Again, these are the sensors on the cell that act as mediators between the antigen that's been discovered and the activation of the immune system. Now, class 1 sensors are present on the surfaces of all nucleated cells. These are like self. Think class 1 is self. Class 2, these are mostly on APCs and B cells. These are all kind of like immune cells. That's because class 1 molecules, and I want to see it now. So class 1 molecules are responsible for handling issues within the cell, issues of the self, right? If something is going wrong in the cell, class 1 is activated and it's handling everything internally. Class 2 handles things externally. So if there is an outside threat coming in, the class 2 molecule is what is activated, and this is starting a much bigger cascade. This is an external problem. And it's a mediator, right? The main function of MHC molecules are to present the antigenic peptides to the T cells. The T cells are kind of the introduction to the adaptive immune system, enabling the immune system to detect and respond to threats. And so, calling for backup. Those SCAT cells, the dendritic cells, and the macrophages, they get something that they know isn't supposed to be there. They travel to the fortress headquarters, which is the lymph nodes, and show all of our T cells what's going on, right? So, like lymph nodes, when you're sick and your lymph nodes get swollen, that is because the APCs have kind of gotten hold of all of those antigens and they've brought them here to be circulated and orchestrate the proper immune reaction. So helper T cells see the poster that is being presented to them by the antigens and the MHC, the APCs, and they send out an appropriate response in the form of cytokines, the IFN gamma, the NFKB, the TNFA. And so here we go, right? This is the real deal, not a drill. we got to get things going here, right? So we've detected something that needs to be taken care of on a bigger scale. Let's bring out the dogs. So this is TNFA, IFNY, ILB, as well as the C-reactive protein. These are all kind of an inflammatory. CRP is an inflammatory marker. The top three, TNFA, IFNY, IL-1B, those are the signals activation. Once those increase, right, the threat has been detected. The natural killer cells are saying, hey, this is too much for me. I need backup. I need help. NFKB gets activated, right? And this is the transcription factor. This is the messenger, the on switch. This is heading to the genes to say, he's flipping the on switch for, I need more cytokines. I need more MHC. I need all hands on deck to get rid of whatever the threat is. So now T cells start to get activated. The APCs are presenting the specific antigens. Now, I've listed the autoantigens, the autoantibodies, GAD, IA2, and zinc transporter 8. These are just examples. There's significantly more. Those three are just specific to diabetes. But the APCs take these antigens and they present them to CD4 plus and CD8 plus T cells. These are two different factions of our immune cells. The CD4 plus cells differentiate into a lot of different things. So CD4 plus is kind of like a project manager, and we'll talk about that in just a little bit. It's reading the antigens and coordinating an appropriate response. CD8 plus cells, they're like hitmen. They get told what's going on and they're like, okay, I know where to go. I'm going to take care of it and kill it myself. So CD4 coordinates an attack. CD8 plus actually executes that attack. So this is special forces here. Those cytotoxic T cells. Cytotoxic T cells is just another name for the CD8 plus. CD8 plus. These warriors identify infected cells that display the invader's antigen, right? They've got the wanted poster. Now they're looking for any of the cells that match that. B cells. These are another faction of our adaptive immunity. So a lot of the times when we talk about the immune system, it's T cells and B cells, not to be confused with beta cells. Different things. B cells, beta cells, different. So B cells are kind of like an assistant to the T cells. So they get instructions from the helper T cells that have made contact with the antigen, and these B cells are able to specialize into plasma cells, and they can start producing antibodies. Antibodies are something that are going to help the T cells identify the threats. So, like I mentioned before, the helper T cells, CD4 plus, are project managers. They are reading what the antigen is telling them, right? Like who they're drawing up the wanted poster. They are coordinating the release of the specific cytokines that are responsible for getting rid of the antigen. And there are a lot of different subtypes that these helper T cells can break into. And we're going to touch on all of them right now just to see the breadth of specificity that our immune system has. So a visual here. CD4 plus on the left, this is a helper T cell. This is coordinating, right? This is who you talk to when you call 911. They're making sure that they're sending out the right forces to handle the right threat. CD8 plus on the right, he's the Terminator. Tell me where to go, I'll kill it. And that's that. So let's talk now about what the different types of T helper cells. So you'll see TH1, TH17, TH35. There's a lot of them. And for the sake of this podcast, I don't want to get too far in the weeds on these. I just want to show you how specific these really are and how incredible the immune system is in general, because it's able to do a lot of different things. So CD4 plus, the T helper cells, they read the antigen that's being presented, right? Like what's wrong? It's being told what's wrong, and it's saying, okay, I've got all these different tools that I'm going to send to take care of this. Th1, right? It's able to create IFNY, TNFA. It's focusing on cell-mediated immunity. It is activating more macrophages, so it's kind of like a cleanup crew, and it's specific to pathogens like viruses and bacteria. Th2, humoral immunity. So it is making B cells that are producing antibodies and involved in the defense against extracellular parasites and allergic responses. Okay, so even right there, you've got one specific to viruses and bacteria, one specific to parasites and allergic responses. Th17, critical in the defense against extracellular bacteria and fungi, and plays a major role in inflammatory and autoimmune diseases. This is just one that correlates with autoimmunity. I'm not sure exactly why, but it's tied with the interleukins, IL-17 and IL-22. The Treg cells, right? This is, and we'll talk about this later on too. How does this immune reaction stop? Tregs, T regulatory cells, are part of that, and they release a certain type of cytokine that deactivate the other cytokines, right? So our immune system has a built-in stop switch, and this is the function of those T regulatory cells. Follicular helper T cells, these help in germinal centers. They enhance antibody production, class switching, and affinity maturation. Again, don't get lost in the weeds on this. This is just another faction of these T helper cells. So T helper 9, allergic responses, asthma, defense against helminths, that's another word for parasites, and they have roles in anti-tumor immunity. So again, we have specific immunity related to cancers as well. Even location. So we've got T helper 22, skin immunity and epithelial barriers. This is like the lining of our gut. This is our skin. These are all kind of like tissues. Interesting to see the specificity. I just thought that was really cool to see. We've got different files, different branches of our immune system for specific threats. So after those T helper cells have been personalized for the threat that we're experiencing, they each have their own cytokine cascade, right? We mentioned before, you see they have specific cytokines related to what they're doing. It's go time, right? So those T helper cells are released. I go to where the threat is, and each of the inflammatory markers has its specific job. So interferon gamma upregulates MHC, class 1 and 2 expression on B cells. The more MHC there are on each cell, the more sensitive that these cells are to T helper cells and cytotoxic T cells. So sensitization is a huge part of this. This isn't just see the threat, kill the threat. This is make sure everyone knows there's a threat here, so they can kind of get ahead of the curve and protect themselves before the threat actually gets there. With more cytokines present, there's more NF-κB. So as the word of the threat gets out in the area, all of them start to kind of turn on their genes preemptively to put themselves in a protective state. Interleukin-1 beta, TNFA, promote local inflammation and induce beta cell apoptosis, right? So in the specifics of diabetes, these particular inflammatory markers are calling attention to the beta cells and initiating the killing off of them. And there are specific interleukins, specific cytokines that are built to recruit more, right? Some actually do the killing, some actually are just kind of signals to bring others in. IL-6, IL-17, they recruit additional immune cells to the pancreas, sustaining the inflammatory environment until the threat is taken care of. Now, in the state of type 1 diabetes, if there is sustained inflammation, this NFKB pathway, the on switches keep getting turned on, right? That the the reverberations of the threat, the inflammation continues to spread. And so everything is super sensitized, everything is ready to be triggered. And again, just touching on that sensitivity aspect of things. This isn't just it's this cell, kill this cell. That cell has neighbors, right? So whenever any cell is under distress, every other cell around it is being put on edge to both guard itself against that threat, as well as make itself ready to be acted on by the immune system in case it also becomes infected or affected. So this activation, the immune system heightens the neighboring cell's ability to identify pathogens to increase the likelihood that the invader is extinguished. We want to make sure that the thing that's in the unhealthy cell isn't hiding someplace in nearby healthy cells. So everything gets sensitized. And so it's basically like falling dominoes. If we aren't able to identify the threat, or if multiple cells are kind of going down, we want to make sure that we get ahead of it. And like a forest fire, you want to put the water down outside the edges of where the infection is to keep it from spreading. So direct beta cell destruction. So once these cells have had all of these cytokines present, the inflammation, everything's getting brought to the scene of the crime. This is where the CD8 plus, the terminator cells come in. They come in, they latch onto the cells. They use something called perforin. Perforin is a molecule that attaches to the cell membrane of the cell and basically opens it up and inserts granzymes. Granzymes are basically like protein degraders. They come in and they disintegrate everything inside the cell so that it isn't able to function anymore and it dies. It focuses a lot on the mitochondria. Mitochondria is the energy source of the cell. So this is like a lethal injection, the CD8 plus. Opens the pore, injects it, mitochondria is dead, cell's dead. It also, there is another pathway of apoptosis, and that's the FAS-L. This is expressed on T cells. Again, this is part of that sensitization process. The unhealthy cell starts expressing more receptors for the signals that are going to tell it to die off. The FAS-L are part of those, are the receptor basically that is like the on switch to have the cell kill itself off. Autoantibodies. So again, B cells are responsible for making those antibodies. They, in the case of type 1 diabetes, they're addressing GAD, glutamic acid decarboxylase, insulin antibody 2, and then zinc transporter 8. There is also an insulin IA2. There's an IAA, insulin autoantibody. There's an IA2 as well. These autoantibodies can participate in the destruction of beta cells through complement-mediated lysis and antibody-dependent cell-mediated cytotoxicity. So these antibodies are kind of accumulating in and around these cells and are basically like road flares, letting everything know, hey, problem's here. They come in and take care of the problem. Now, an interesting point specific to GAD, and I talk about this in episode 40, but autoantibody production for things like GAD imply that there's something going on with the beta cells before those antibodies are produced and the immune system is reacting, or the adaptive immune system is reacting. So that's because GAD is an intracellular protein. In a healthy body, there's no GAD being thrown around in the body humor. It's not in the blood, it's not outside the cell. So in order to have antibodies, in order for B cells to be able to form antibodies against GAD, it needs to be outside the cell. And so the idea that, oh, well, we have antibodies and that's why the immune system is reacting doesn't get the whole picture, because how is GAD getting outside the cell in the first place? There's something that caused a leak in the membrane of the beta cells that let GAD out of the cell. And so we don't know why. Not a lot of people are talking about how this is going on. They're just kind of like being told, hey, you have got GAD autoantibodies, you're at risk for diabetes. But it could be either externally initiated or it could be internally initiated. There is some sort of immune reaction happening on the outside. It could be some sort of pathogenic attachment on the beta cells. The immune system is acting, and GAD, which is the little red X's, are being let out. Then the antibodies are formed. Could also be happening inside, right? There could be some sort of mitochondrial stress, something wrong is happening inside the beta cell. The innate immune system happening inside the cell is not able to fix it. The membrane undergoes self-lysis, kills itself off, and then the GAD's being spilled and the antibodies are formed. Again, not sure why or what the condition is. It could be either or. You're not sure. But either way, all of this inflammation is going on at the same time. It's not being handled to completion, right? It just kind of keeps going. So you've got a ton of NFKB in circulation. Everyone's on switch for being sensitive to inflammation is being turned on. IL-6, IL-17 keep recruiting more immune cells. The problem's not going away. And so everything kind of keeps getting recruited more and more and more and more and more. Each existing or newly regenerated beta cells, even the healthy ones, are being exposed in this cytokine-rich environment, right? You could be a perfectly good house, but if your entire cul-de-sac is on fire, you're going to be taking on a lot of smoke, and you're going to be feeling the heat. And when that happens, you're becoming more susceptible to reaction by the immune system as well. So each new immune reaction is increasing the chances of an immune reaction, because you're going to have more MHC receptors on your cells. You're going to have more fast ligands, which is the signal like, hey, if you need me to die off, let me know. Those are all getting upregulated in this state of chronic inflammation. And because of this, the beta cells are being killed off. So over time, this sustained autoimmune attack leads to significant loss of the function of beta cells. The fewer beta cells you have, the less insulin you have. The less insulin you have, the less your blood sugar is regulated, and you devolve into the state of type 1 diabetes. Now, that doesn't mean that you have no beta cells. It doesn't mean that your beta cells aren't replicating anymore. It's just that it's like being born into warfare. You just have this constant state of craziness around you where it's very hard to thrive. Now, where's the off switch on this thing? In this whole state of affairs, being born into warfare, where's the off switch? how do we get this to stop? What does stopping look like in a healthy system? And we mentioned regulatory T cells before, or Tregs. They play a crucial role in maintaining immune homeostasis. They're the ones saying, okay, the threat, I think we've done a pretty good job of taking care of that. I think we can start to cut back now. And that's when the cytokines start to disappear. Everything starts to kind of like calm down and you can return to normal. So regulatory T cells are made in these bone stem cells. They are developed and matured in the thymus. The thymus gland is kind of in the middle of your chest. They typically express the transcription factor FOXP3. Their primary role is to maintain immune tolerance and prevent autoimmune diseases, right? Autoimmune diseases are basically an immune system with no Tregs, right? It's an immune system with no stop switch. So for those with autoimmune conditions, is it a dysfunction, or is it a dysfunction or deficiency of Tregs? Do we just not have enough off switches? The science has explored more Tregs to help calm the autoimmune loop. It's used in transplants to help basically suppress the immune system. So there's some potential there for treatments. And they do it in a couple different ways. This is interesting to me. So they secrete their own cytokines. So we talked a lot about IL-17, IL-6, IL-2, IL-1 beta. Tregs make their own. So IL-10, TGF beta as opposed to TGF-A, IL-35. These are all cytokines designed to stop the immune reaction. So they're basically like riot control. You're letting these out. They're kind of like, hey guys, we gotta calm down. They're down regulating everything to make sure that things don't go off the hinges. Cell contact mechanisms. So the Tregs can actually link up with things like natural killer cells, the helper T cells, as well as the cytotoxic T cells, and stop it from reacting. Right? So it basically binds and neutralizes the killer cells and prevents them from killing too much. Or if there's too many to begin with, right? It's like, hey, we were at a level 8, we're at like a level 2 now. So all this extra stuff, you guys got to go home. Binds them and neutralizes them. As well as metabolic disruption. So Tregs can eat the fuel of the other T cells and B cells. So basically cuts off the oxygen supply for the T cells to do their job. So this is where the loop comes in. So what are the ways that our immune system just keeps running and running and running? So it's either the T regulatory cells aren't able to properly shut down the CD4 plus and the CD8 plus. Right, so those helper T cells and those cytotoxic T cells just are out and about. And I mentioned before, like, okay, maybe we had a threat that was like a level 8 or a level 9. And so we put a lot of T cells into circulation, a lot of cytokines. Once that threat starts to die down, Tregs are how we tell those ones to go home, the extras to go home. But if Tregs aren't able to get that message out, we've got 8 levels of immune protection circulating for a level 2 threat. So it's too much. Or we've got newly regenerated cells that continue to show signs of weakness and dysfunction. So is the autoimmune loop, where we're kind of like pinning it on the immune system, what if it's actually our cells are just keep making dysfunctional cells? So this isn't really the immune system's fault. It's just that threats just keep getting produced. It's not like, oh, our immune system's reacting when it shouldn't. It's like, no, there's just always a threat. Why is there always the threat here? And so, is there actually a threat? If there is, we need to think from a nutritional standpoint, what are the raw materials that we need to supply our cells in order to produce functional cells? And if these cells are being wrongfully targeted, we need to consider pathogenic, because one of the ways in which viruses, bacteria, parasites act is by mislabeling cells. They're trying to evade detection by our immune system. And so they hide by molecular mimicry. They stash themselves in healthy cells. And so, these cells may be wrongfully terminated. And as our adaptive immunity works, right, it's able to identify threats. Once it neutralizes that threat, then it kind of always keeps memory T cells, which are another subset of T cells that remember the threat from before, so that it can basically have a shortcut to the appropriate immune response. What if our adaptive immunity has, over time, because of this persistent inflammation, become rigid in its identification of beta cells as a threat, right? For the time where you were developing type 1 diabetes and leading up to your diagnosis, were your beta cells always inflamed, that our immune system has been like, I guess that's beta cells now. And so anytime it sees a beta cell, it's identifying it as a threat. So there's a couple different scenarios we can touch on. First one, this is the one I've focused on the most. Nutritional deficiency and imbalance leaves our cells malnourished, internally inflamed, and unable to regulate themselves. This leaves beta cells vulnerable to immune reactions designed to heal, but without resources to effectively do so, right? So there's something wrong with the beta cell itself. Our immune system comes in to address it, but doesn't have the tools to actually fix anything. And the beta cells that are regenerating are dysfunctional as well, because they don't have the necessary nutrients to heal. And then second scenario, pathogens invade our body. This could be COVID, Lyme's disease, parasites, Epstein-Barr virus, all different kinds. They hijack our cellular mechanisms to preserve their ability to replicate, right? That's the virus's job, is just to pass on its progeny, and negatively influences our natural immunity. So it either has convinced our immune system that, hey, I'm not the problem, you got to go attack this thing, or it's actually messing with the signals of our immune system. So now when it's time to activate something, those pathogens have cut off those phone lines and they're not able to effectively communicate. And so all of this inflammation accumulates in the wrong places. Possible scenario 3. And this is just a sheer dysfunctional immune system. Our immune system is unable to identify self from foreign, and it just happens to attack beta cells. Regulatory T cells are underutilized, so we're all gas, no brakes, and the body is unable to contain the loop of cytokine production. Everything just kind of keeps going in the wrong direction. And then our adaptive immunity has molded itself into this dysregulated state. Or it could be a combination of all three. And I welcome you to entertain all three options. So here are some specifics for scenario 1. We're nutritionally deficient, whether it be iron overloaded, magnesium deficient, copper deficient, fat soluble deficient, whatever. Our mitochondria are not able to function in the beta cells. The cell membrane is not able to contain the contents of the cell, right? With the GAD autoantibodies. Something is happening inside where it's spilling. It's spilling out into the open. Could be an endoplasmic reticulum failure. So the ER is a particular important organelle in beta cells. If it does not do its job in terms of handling the reactive oxygen species inside that cell, it does not go well for the cell, and the cell ends up killing itself off. So with all of these issues inside that beta cell, it starts to accumulate those reactive oxygen species until the cell fails and spills its contents. What was once an internal struggle of the beta cell has now become externalized. The inside problem is now an outside problem. And with an outside problem, there is a much greater immune system at play. The sensitization to this immune reaction for the outside problem now causes any struggling or near-death beta cells to become sensitized to this immune reaction. And because they're all struggling, because there aren't enough resources to live properly, they all die off. They all start to go. And so this immune system acts on the beta cells, becomes adapted to the idea that beta cells just aren't healthy enough to stick around, so we got to get rid of them. And then you kind of just keep going on this loop, no matter how many beta cells you regenerate. So the cell does not have the nutritional means of repairing the damaged tissue to the point where the immune system can be deactivated. That's as succinct as I can get. Scenario 2, we get infected. You name the pathogen, it could be anything. The pathogen initiates an immune cascade. It has adapted specific means to evade capture. It's camouflaged itself within our typical body system. And by evading termination, it is now replicating at will and leaves our body vulnerable to an immune system that knows that there's a threat. It knows there's something wrong. It's like, I can't really tell where it is, but I know it's here. So you're getting the activation aspect of things, but without any results, right? So it's able to identify the threat, but not isolate it or end its replication target or replication cycle. And now beta cells are particularly at risk and susceptible to the overabundance of these cytokines and inflammatory markers. And scenario 3, I didn't want to spend too much time on this just because I personally do not think that this is really viable. Our immune system is so ingrained in so much of our body and functions properly in like 99.9% of scenarios. I to this day cannot find out what makes beta cells the sole target of an autoimmune dysfunction. Right? Why would regulatory T cells be able to regulate basic cell function, right? Every day of your life, there are cells dying off, there are cells being reborn, things are being recycled and reused. We're able to live, right? That's not, if your immune system wanted you dead, you'd be dead in a second. But it just so happens to fall on this one cell type. It doesn't make any sense to me. But that being said, we can use parts of this scenario to make sense of it as a whole. So think of the adaptive immunity, right? The fact that our immune system does adapt to the conditions it's living in. And if those conditions that we're living in are less than functional, the immune system is going to be chronically on and targeting what is chronically dysfunctional. Okay. And then the misidentification of self. There is something going on where our immune system thinks that, it mistakes the wanted poster for a mirror, and it's attacking itself. Possibility? Yes. Likely? I don't think so. But so what we really need to do is look at all three of these and combine the factors into one. and that's where I'm at now. A body nutritionally compromised is a body that is vulnerable to opportunistic invaders, right? So we have unstable cellular mechanisms. It's not just beta cells that aren't able to do their jobs. There's a bunch. DNA repair mechanisms. Our body, every cell in our body has the innate knowledge to repair damage done to the DNA. However, it needs the necessary amino acids, the necessary carbs and fats in order to build these tools. If it does not have these things, it cannot do them properly. So DNA repair, membrane integrity, mitochondrial efficiency, all these things are being compromised because our cell doesn't have the tools it needs to rebuild and repair. Because our body is in this state of always having to fix something, but never actually having anything fixed, pathogenic infection comes in. It's opportunistic. It sees that there are holes in our defense system and is like, I want to live in that body. It's designed, those infections are designed to hijack our natural processes to preserve their ability to replicate at the expense of the host. An immune reaction initiated to address either the nutritional deficits or the pathogen presence, it doesn't have the means to complete the job. So it's acting on the problem, can't complete the job. And it's either because the invader is camouflaged in our body system, so it doesn't really know what it's looking for. And so somehow our adaptive qualities of our immunity are now fixed in this rigid state where everyone is being told, hey, beta cells are trash. Beta cells are, you got to be careful of beta cells. If you see a beta cell, you got to lock them up. When really they just needed more raw materials. So that's kind of where we're at. When it comes to fixing this issue, this deep-seated issue, number one, address those nutritional deficiencies. Supply your cells with the raw materials it needs to build the proper mechanisms, right? Lipids, amino acids, carbohydrates. These are all things that our cell needs in order to build properly. This comes down to minerals, those macronutrients I just mentioned, vitamins, supplements, plant compounds, what have you. They're all designed to help our body put itself back together. We need to exterminate the pathogens, right? Get rid of those parasites, get rid of the virus, get rid of the bacteria, break those replication cycles. Make the viruses, make our body an inhospitable place to those viruses, right? Patch up the holes in our immunity and break the inflammatory cycle. Reclaim the systems, right? GABA and GAD, that nervous system regulation aspect of GABA is completely taken over with certain virus infections. So we need to reclaim the systems that have been taken over by viruses and bolster our natural immunity, right? Antioxidant use, natural ways to increase our regulatory T cells. Those are the off switches. We need more off switches in order to stop the loop. We also need to decrease, possibly, the effector T cell sensitivity. Like why are our cells so heightened and ready to be turned on for extermination? Again, I see number one as being at the root, right? But all of these come into play and all of these need to be paid attention to. So now for the visual learners, I have created this little flow chart here for mapping out how the immune system works. Okay, so we're going to work from left to right here, blue to red. Now, we'll zoom in here, and this is such a cool service. I use a service called Miro Board, where I can kind of create these flowcharts. Just cool little tool. Now, let's read out. APCs are engulfing an antigen. We start with an antigen. There's something in the cell that is not functioning properly. They are taken in by the dendritic cells or the macrophages. They're kind of identified as a threat, swallowed with the little wanted poster, and they bind to and express MHC molecules, the major histocompatibility complex, right? So they are taking these cells to all of the different T cells that they have available to them. Now, remember, MHC class 1 molecules are for internal issues. MHC class 2 molecules are from external issues. So inside the cell problems, class 1, outside the cell problems, class 2. Now, first things first, the natural killer cells come into place, right? Those are the ones, the local sheriff just taking care of things, making sure that, you know, if it's a small problem, it's handled internally, doesn't make a big deal. So these natural killer cells are able to elicit all of these different cytokine markers. Again, the T helper cells, the interleukins, TNFA, IFNY, they're all there, okay? So these natural killer cells can elicit these, which create their own immune response. They can make CD4 plus T cells. They can also formulate the killer cells. Now, if it's internal and it's a small problem that can be handled internally, it's a natural killer cell. It creates these cytokines. These cytokines activate the killer cells. It's killed off in the cell immediately. There's no need to orchestrate this big reaction through the CD4 plus. We don't need to call 911 for something that we know how to handle inside the cell. That's where we just bring in the killer cells. Everything's taken care of, and it's brought through this whole cascade that results from those CD8 plus cells, the killer cells. And we'll touch on that in just a little bit. So in the case where natural killer cells are not able to effectively handle the antigens that are being presented by the APCs, that is when we have CD8 plus and the CD4 plus molecules being initiated. Now, like I mentioned before, if it's a problem within the cell, you're getting killed off immediately, right? That cell's trying to save itself from getting to a point where it starts to spread damage to its neighbors. If the threat is coming from outside the cell and we need the adaptive immune response to come into play, that's when we get to the CD4 plus. Those are the helper T cells. So antigen presents, APC swallow it up and bring it to our T cells, right? Natural killer cells are like, this is beyond my realm. I can't take care of this. I need help. The helper T cells come in. Now, this is all being done through our lymphatic system. So the lymph system is taking the threats. It's being read and determined what it is and what the reaction needs to be. And it starts, sending out the correct helper for the correct antigen. So you have differentiation into all these different types of T helper cells and cytokines, the increase in NFKB activity to make sure that all of our neighboring cells have their genes turned on to be able to create these as well in case of an emergency. Once we have all of these, that's when the threat is actually being taken care of, right? It's making sure it's marking things appropriately. If the threat continues to be a threat, you have all of these IFN gamma, TNF alpha. They can create more CD4 plus cells, so they can call in for more help and more help and more help. You can even have loops within here. So like we learned that IFN gamma can call in more molecules, right? More TNFA, more IL-1B. So these can kind of create their own little loop of needing more and more backup. Now, it can even call, see here with that TNF alpha, this can go all the way back to the antigen presenting cell. So this can be like, hey, listen, we've got new antigens in here. We need to make sure we get you in here to handle the threat that we weren't, if they are sent in for the wrong problem and they're like, hey, I don't have the right tools for this, they can also activate more APCs to initiate a new helper T cell reaction. So this is where all that inflammatory damage is being caused. The more of these there are, the more general inflammation there is. Once these have identified the problem and gotten rid of, addressed the issue, and things are starting to be taken care of, or they know exactly what cells need to be killed off, they activate the killer T cells, the CD8 plus. Now, CD8 plus, because it knows it's going to be like getting its hands dirty in an unhealthy cell, CD8 plus cells can also activate the release of more inflammatory markers, right? If it's, killing off one cell, but 8 cells need to be called off or killed off, it's calling for more through these inflammatory markers. So now let's talk about how these killer cells are actually killing. So killer T cells are creating cytotoxic T lymphocytes, and these are basically special subsets of killer T cells that have specific mechanisms for how the cell is going to be killed. These CTLs are what are binding to the cells that need to die, acting on it by attaching with perforin, which opens the pore and injects the granzymes. So the granzymes are what are kind of like jumbling the inside so that the cell gets killed off. So now apoptosis, which is die off, is happening. The pathogen can either be cleared, right? So it's like, okay, hey, we've cornered the issue. This is the issue. Kill switch activated. You have the cell die off. You have that killer T cell kill. The threat's neutralized, right? That's kind of like an immediate boom. Everything's taken care of. Don't worry about it. You also have the memory killer T cells. These are long-term protection. So now that you know the cycle, now that you've kind of run through this whole thing for a particular antigen, this whole sequence is going on for every new antigen every time. So once you've gone through this sequence, now you have these memory T cells that are going to copy and paste what has gone on to address this new antigen for the new antigens to present, that come later on. This is the mechanism behind like vaccinations, right? You give a weakened antibody, your body goes through the necessary sequence, remembers the necessary sequence so that the next time anything comes around, it knows what to do. Now, what happens if after that killer T cell is activated, it induces that cell death, but somehow the pathogen persists, right? This is the case of, a virus that, molecular mimicry has kind of like evaded capture. What happens then? So we follow this loop. See if I can use this. Pathogen persists. We're going all the way back to call for our helper T cells, right? It's like, oh wait, the threat's still here. Make sure we have, the correct antigens being distributed. Now, if we go back and the pathogen actually is cleared and things are being taken care of, now we start to release those regulatory T cells, right? And these T cells are making the specific cytokines that are meant to neutralize and to calm the immune reaction. So IL-10, TNF-beta, IL-35, These are all designed to neutralize the inflammatory cytokines. These are designed as well, you see those regulatory T cells, these are designed to halt those CD4 plus T cells. And they can also induce apoptosis in the killer T cells. They're making sure they're clearing the space of all of the extra inflammatory molecules. So I hope this graph was helpful. Again, this is being done for the presentation of every antigen. The fact that we have the long-term protection via our memory B cell or T cells rather, this abbreviates, this going on after we've learned what the antigen is. But in terms of like learning and finding out how to react to these new cells, antigen presents, APC identifies it and brings it to the natural killer cells. Natural killer cells elicit their antibodies, their cytokines to kill off the antigen. If it's unable to do that, that is when we start to interact with the MHC molecules and we get the help of our helper T cells, the 911 service, as well as the terminators, the killer T cells. Those killer T cells, those CD4 plus cells, they start this kind of chain reaction of getting those cytokines activated. Those cytokines are designed to do very specific things against specific antigens. Once they act on them, they either go to completion with the killer cells and finishing them off, or it continues that loop and has to continue asking for more and more helper T cells to elicit proper immune responses. So this is kind of where that autoimmune loop happens, right? We're always kind of in this area here of acting on the pathogen, but never actually killing the pathogen. And so we're constantly being sent over and over and over into a state of needing to address this ever-present antigen. All right. So I hope this was helpful. I love making flowcharts like this. This is really helpful for me to walk through everything. And this is nice to be able to see everything we just talked about and transpose it into something visual and a little bit more concise. All right. So I hope you like this. And so with that, we now have a full picture, a better understanding of how our immune system is operating in a state of autoimmunity. What are the things in motion here that we need to pay attention to when it comes to addressing the roots of type 1 diabetes? We've got a list out of all of the major players that we need to be paying attention to from the side of inflammation. We know the soldiers that we kind of have on the battlefield fighting against these pathogens, against these imbalances and inflammatory markers, right? We've got, the T regulatory cells, IL-10, TNF beta, all of those good guys working to turn our autoimmune loop off. We've also got the visual demonstration, right? I hope you enjoyed that mural board where we got a chance to kind of actually look at things mapped out, how they relate with all of the other pieces. And it's always just nice to have a visual representation. So I can't thank you enough for being here. This is episode 43, Diabetics for Diabetics Radio. I'm always looking for as much support as I possibly can get. Sharing with someone who has type 1 diabetes or who is responsible for someone who has diabetes. You can purchase supplements, Thorne Research, MitoLife, Ancient Bliss. Those are companies that I trust. Those are the ones that I use when it comes to supplementing my mineral deficiencies, my vitamin imbalances, what have you. I also have educational material as well that will all be linked in my description. All of the support you can get is much appreciated. Make sure you subscribe, follow. And with that, episode 43, mapping out autoimmunity and type 1 diabetes is all done. Thank you so much and enjoy the rest of your day.